picture a copper wire, 1 millimeter thick, a few centimeters long. Ordinary. Unremarkable. Now picture what's inside it. Copper atoms are packed together in a crystalline lattice, each one about an angstrom apart. That's 10 billionths of a meter. In that tiny wire, you have roughly 10 to the 22nd atoms, 100 billion trillion obstacles stacked in every direction, filling every available space. There is no room. There are no gaps. The wire is not hollow. It's a solid wall of atomic nuclei, each one surrounded by a cloud of electrons, each cloud overlapping with its neighbors. If you were an electron trying to cross that wire, you'd be navigating a forest so dense that you can't see past the first row of trees. And yet, when you connect that wire to a battery, current flows. Electrons move from one end to the other. Somehow, billions of trillions of them every second, threading their way through an atomic maze that should be impenetrable. You've been told this works because the electrons are free. That's the word. Free electrons. As if the metal releases them, as if they're no longer bound to individual atoms, as if they can just drift through the material unimpeded. But free to do what? Free to move where? An electron in copper is still surrounded by atoms. It's still immersed in a chaotic storm of positive charges and overlapping electron clouds, and those atoms aren't stationary. They're vibrating, jiggling with thermal energy. The lattice is never still. Every atom is a moving target, oscillating randomly, and the electron has to pass through all of them. By any classical reasoning, the electron should collide with an atom almost immediately. It should scatter, ricochet, lose its direction. The mean free path, the average distance it can travel before hitting something, should be tiny, a few angstroms at most. But experiments tell a different story. At room temperature, electrons in copper travel for hundreds of angstroms between collisions. At low temperatures, thousands. In the cleanest samples, at near absolute zero, the mean free path stretches to millimeters. Millions of atomic spacings without a single collision. The electron is passing through a densely packed lattice as if the atoms aren't there. This is not a minor puzzle. This is the central mystery of electrical conduction. The wire is full. The path is blocked. And yet, somehow, the electron sees it as empty. In 1900, Paul Drude tried to explain conduction with a simple model. He imagined the electrons in a metal as a gas, free particles bouncing around randomly, colliding with atoms every so often, drifting slowly in the direction of an applied electric field. Like ball bearings rolling through a pinball machine. Random motion, occasional collisions, net drift. And remarkably, this model works. Sort of. It predicts Ohm's law. It gets the relationship between current and voltage right. It explains why thicker wires have less resistance, why longer wires have more. It even gives you a formula for conductivity that matches the measurements reasonably well. Physicists loved it. It was intuitive, mechanical. You could picture it. Electrons as little balls, atoms as obstacles, collisions as the source of resistance. Simple. But then you check the details. Drude's model says the electrons should collide with atoms constantly, every few angstroms. And if that's true, then the average speed of an electron, its drift velocity, should be enormous. Meters per second, maybe faster. So you measure it, and the actual drift velocity is about 1 millimeter per second, sometimes slower, glacial. An electron in a wire carrying a decent current takes minutes to travel a single centimeter. That's the first problem. Here's the second: heat capacity. If the electrons are a gas, bouncing around with thermal energy, then they should contribute to the heat capacity of the metal. When you heat up copper, you're adding energy to everything in it, the atoms and the electrons. And if the electrons are free, behaving like a gas, they should absorb a predictable amount of that energy. Drude's model predicts they should contribute significantly, but experimentally, They barely contribute at all. The heat capacity of metals is almost entirely due to the vibrating atoms. The electrons act as if they're not even there. And then there's the third problem, temperature dependence. Drude said resistance comes from collisions, more resistance. At higher temperatures, the atoms vibrate more, so you'd expect more collisions, and that part actually matches. Experiment resistance does increase with temperature. But if collisions are what matter, then at low temperatures, when the atoms are barely vibrating, resistance should drop smoothly toward some small value. It should never go to zero, except in some materials it does. Superconductors have zero resistance, not low resistance. Zero. Electrons flow without any collisions whatsoever. Drude's model has no explanation for this. It can't even begin to address it. So the model works just enough to be useful, but it's built on a foundation of lies. The electrons aren't colliding the way Drude said. They're not drifting the way he predicted. And the atoms aren't obstacles in the way he imagined. He got the right answer by accident, by assuming things that aren't true and canceling out errors that shouldn't have canceled. The real question is, if the electrons aren't bouncing off atoms like classical particles, then what are they doing? You need to stop thinking of the electron as a thing with a position. That's the root of the confusion. You imagine a tiny ball, a point charge, traveling through the metal, dodging atoms or bouncing off them. A trajectory, a path, classical mechanics. But an electron is not a particle, not in the way you think. An electron is a wave, a quantum wave. It doesn't have a definite position until you measure it. What it has is a wave function, a spread-out probability distribution that extends through space. And when that wave encounters an obstacle, it doesn't collide the way a ball collides with a wall. It scatters, or it doesn't. And whether it scatters depends on the structure of the obstacle and the wavelength of the wave. This is not a metaphor. The electron literally behaves like a wave. You can demonstrate this in a lab. Fire electrons at a double slit, and they produce an interference pattern. Not because each electron is interfering with other electrons. Each electron interferes with itself. It passes through both slits simultaneously as a wave, and the two paths overlap and interfere on the other side. So when an electron moves through a metal, it's not threading a path between atoms. It's a wave propagating through a medium. And the atoms aren't discrete obstacles. They're part of the potential landscape that the wave experiences. Now here's where it gets strange. Waves scatter off obstacles, yes, but they don't scatter the same way particles do. A particle sees an obstacle and bounces. A wave sees an obstacle and diffracts around it, and whether the wave is scattered or transmitted depends on the relationship between the wavelength and the size and spacing of the obstacles. Think about sound. Long wavelength sound bass notes bends around corners and passes through gaps easily. Short wavelength sound high-pitched notes scatters off small objects. The wavelength determines what counts as an obstacle. For an electron in a metal, the wavelength is set by its momentum. And it turns out that the de Broglie wavelength of a conduction electron, the wavelength of its quantum wave function, is on the order of a few angstroms. That's the same scale as the atomic spacing. So the electron wave isn't much smaller than the gaps between atoms. It's not squeezing through, it's washing over the entire structure. And the question isn't whether it hits an atom. The question is whether the atomic lattice as a whole scatters the wave or lets it through. And here's the key. A periodic structure does something special to waves. If the atoms are arranged randomly, the electron wave scatters chaotically. Every atom contributes a scattered wave in a random direction, and the total scattering is a mess. The wave is destroyed. It doesn't propagate. But if the atoms are arranged in a perfect, repeating lattice, the same spacing, the same orientation, over and over, then something extraordinary happens. The scattered waves from each atom interfere, and if the periodicity is just right, they interfere constructively in certain directions and destructively in others. In fact, in a perfect lattice, the scattered waves can cancel completely in the forward direction, leaving only the transmitted wave. The electron wave passes through as if the atoms aren't there, not because the atoms moved, not because the electron avoided them, but because the quantum interference erased the scattering. This is what Feynman understood. Conduction isn't about electrons avoiding atoms. It's about the atoms conspiring through their perfect arrangement to become invisible to the electron wave. Let's be precise about what happens. An electron wave enters a metal. It encounters the first layer of atoms. Each atom scatters the wave, sends out a spherical wavelet in all directions, just like we saw with glass. Same physics, same quantum interference. But now consider what happens when the wave hits the second layer of atoms, and the third, and the fourth. Each layer is scattering the wave, each atom is contributing, and all of these scattered wavelets are overlapping, interfering, creating a fiendishly complicated field. In a random arrangement, this interference would be chaotic, destructive everywhere. The wave would die. The electron wouldn't propagate. You'd have an insulator. But the atoms in a metal aren't random. They're locked into a crystalline lattice. Face-centered cubic for copper, body-centered cubic for iron, hexagonal close-packed for magnesium. The exact structure varies, but the key is that it's periodic. The same pattern repeats, unit cell after unit cell, billions of times across the material. And periodicity changes everything. When the electron wave scatters off the first atom, it creates a wavelet. When it scatters off the second atom, one lattice spacing away, it creates another wavelet. These two wavelets are out of phase by an amount that depends on the lattice spacing and the wavelength of the electron. Now here's the trick. If the wavelength and the lattice spacing are matched just right, the scattered wavelets from every atom interfere destructively in every direction except forward. The wave scattering backward cancels. The wave scattering sideways cancels. The wave scattering at an angle cancels. The only thing left is the forward propagating wave, reconstructed by the constructive interference of all the transmitted pieces. This is called Bragg's condition, and is the same reason X-rays diffract off crystals in specific directions. The lattice acts as a diffraction grating for the electron wave. But there's something deeper here, something Feynman emphasized. The electron wave doesn't just pass through the lattice. It's not avoiding the atoms. Every atom participates. Every atom scatters the wave. But the collective result of all that scattering, when you add up the contributions from trillions of atoms, all of them perfectly spaced, is zero. Zero scattering, not low scattering. Zero. The atoms are there. The electron wave interacts with them. But the net effect, after interference, is as if the lattice weren't there at all. Feynman called this the absence of scattering. Conduction happens not because the metal is full of empty space, but because the structure of the metal makes scattering impossible. The electron wave propagates freely, not because there are no obstacles, but because the obstacles are arranged in such a way that their scattering contributions cancel. This is a quantum conspiracy on a macroscopic scale. Every atom has to be in the right place. The periodicity has to be perfect. The electron wavelength has to match. If any of these conditions breaks down, the conspiracy fails and scattering returns. And this explains something Drude could never explain, why conduction is so sensitive to imperfections. At a single impurity, one atom of the wrong type in the wrong place, and the periodicity breaks. That atom scatters the electron wave, and the scattered wave doesn't cancel, it radiates. The electron loses momentum. That's resistance. Add a dislocation, a line defect where the lattice is misaligned, and same thing. Scattering returns. Add a grain boundary, a place where two crystal domains meet at an angle, and the periodicity is broken there too. More scattering. The metal doesn't conduct because it's empty. It conducts because it's perfect. And any deviation from perfection, no matter how small, brings the atoms back into view. The electron wave stops seeing through the lattice and starts colliding with it. Now we get to the most brutal part. A metal at absolute zero, if you could ever reach it, would be a perfect conductor. The lattice would be frozen, every atom locked in place. Perfect periodicity. The electron wave would propagate without scattering, zero resistance, but you can't reach absolute zero. And even if you could, the moment you put current through the wire, you'd heat it up. At any temperature above zero, the atoms vibrate. They're not sitting still at their lattice points. They're oscillating. Each atom is jiggling around its equilibrium position, driven by thermal energy. And the vibrations are random. One atom moves up while its neighbor moves down. One moves left while another moves right. The phase of each vibration is uncorrelated, and that randomness destroys the periodicity. The lattice is no longer perfect. It's no longer a repeating pattern with every atom in exactly the right place. The spacing between atoms fluctuates. The alignment shifts. And from the perspective of the electron wave, this means the interference no longer cancels perfectly. The atoms become visible again. Not all of them, not all at once, but statistically, some of them. The electron wave encounters a thermally displaced atom, and instead of perfect cancellation, there's a net scattered wave. A little bit of momentum is transferred to the lattice. The electron loses coherence. That's a collision. This is what resistance is, not electrons bouncing off stationary atoms like billiard balls. Electrons scattering off deviations from perfect periodicity caused by thermal vibrations. Physicists call these vibrations phonons. Quantized sound waves in the lattice. The electron wave interacts with the phonon field, and when it does, it scatters. The stronger the thermal vibrations, the higher the temperature, the more phonons there are. And the more scattering occurs. That's why resistance increases with temperature, not because the atoms are in the way more often. Because the lattice becomes less perfect, and the quantum conspiracy breaks down. And here's the disturbing implication. At room temperature, the atoms in a copper wire are vibrating with an amplitude of about 1/10 of an angstrom. That's a tiny displacement, a few percent of the atomic spacing. But that's enough. That tiny deviation from perfection is enough to make the electron scatter every few hundred angstroms instead of propagating forever. Conduction is that fragile. Now consider what happens if you cool the metal down. The thermal energy decreases. The atoms vibrate less. The lattice becomes more perfect. The electron wave scatters less often. Resistance drops. At liquid nitrogen temperatures, 77 Kelvin copper's resistance is a fraction of what it is at room temperature. The mean free path stretches to microns. The atoms are still vibrating, but barely. At liquid helium temperatures, 4 Kelvin resistance drops even further. The lattice is almost frozen. The electron wave can propagate for millimeters without scattering. And in certain materials, at low enough temperatures, something even stranger happens. The resistance doesn't just drop, it vanishes completely. The material becomes a superconductor, and the electron wave propagates without any scattering at all forever. But that's a different story, a different quantum conspiracy involving electron pairing and coherent quantum states. We're not going there. What matters here is this. Normal conduction, the conduction you rely on every time you turn on a light, only works because the quantum interference survives despite the thermal chaos. The lattice is never perfect, but it's close enough. The atoms vibrate, but not so much that the periodicity is destroyed. You're conducting electricity on the edge of disorder. One more kick of thermal energy, one more impurity, one more defect, and the whole thing collapses. So if conduction is about electron waves propagating through a periodic lattice, why doesn't everything conduct? Why is copper a conductor and rubber an insulator? They're both made of atoms. They both have electrons. They both have some kind of structure. The answer has nothing to do with whether the electrons can move. The answer is about where they can go. In a conductor, the electron states near the Fermi energy, the highest occupied energy level, are only partially filled. There are empty quantum states right next to the filled ones. An electron can absorb a tiny amount of energy from an electric field and jump into a nearby empty state. It can change its momentum. It can propagate. But in an insulator, the situation is different. The electrons fill up all the available states in what's called the valence band. Every state is occupied, and the next available states, the conduction band, are separated by an energy gap, a forbidden zone. No states exist there. To move an electron in an insulator, you'd have to give it enough energy to jump across that gap. For most insulators, that gap is several electron volts, huge on the scale of thermal or electrical energy at room temperature. So the electrons are stuck, not because they're bound to individual atoms, though that's part of it, but because there's nowhere for them to go. The quantum states are full, and the empty ones are unreachable. This is the band gap, and it's a purely quantum phenomenon. It emerges from the way electron waves interact with the periodic potential of the lattice. When you solve the Schrödinger equation for an electron in a periodic lattice, you don't get a continuous spectrum of allowed energies. You get bands, ranges of energy where solutions exist, separated by gaps where they don't. In a metal, the bands overlap, or the highest band is only partially filled. Electrons can move freely between states. The lattice becomes invisible, just like we said. In an insulator, the bands are separated. The filled band is full. The empty band is empty, and there's no way to move an electron without jumping the gap. So insulators don't conduct, not because the atoms are in the way, but because the quantum mechanics of the system forbids it. The electron wave doesn't scatter off the atoms. It just has nowhere to propagate to. And here's the thing that should bother you. The only difference between a conductor and an insulator is how many electrons the material has and how the energy bands line up. Carbon, in the form of diamond, is an insulator, one of the best. A huge band gap, electrons locked in place. But carbon, in the form of graphite, conducts, same element, same atoms, different structure. The bands overlap. Electrons can move. Silicon is an insulator at low temperatures, but add a tiny bit of phosphorus 1 impurity atom per million, and it becomes a semiconductor. The impurity donates an electron into the conduction band. Now there are states to move into. Now it conducts. The distinction isn't fundamental. It's structural, quantum mechanical, a detail of how the electron wave functions interact with the lattice. Metals conduct because their electrons have somewhere to go, and the lattice lets them see nothing. Insulators don't conduct because their electrons have nowhere to go, even though the lattice is just as transparent, just as periodic. Both materials are honest about what they are, but only the metal admits the electron wave into the game. Let's take this to the end. When you flip a light switch, you think you're sending electrons down a wire, pushing them from the battery, through the circuit to the bulb. A flow, a current, cause and effect. But nothing flows. The electrons were already there. They're always there, filling the metal, occupying every available state. What you're doing when you apply a voltage is shifting the entire distribution. You're nudging the quantum states, tilting the energy landscape, and allowing the electron waves to propagate slightly more in one direction than the other. The drift velocity, the actual speed at which this net propagation happens, is glacial. Millimeters per second. An individual electron might take an hour to cross a wire that lights up a bulb instantly, but the signal the electromagnetic disturbance. The coordinated shift in the electron wave distribution propagates at nearly the speed of light. Not because electrons are racing through the wire, because the quantum state of the entire system shifts coherently. And that shift only works because the lattice is invisible. If the atom scattered the electron waves, the signal would die. The disturbance wouldn't propagate. The bulb wouldn't light. Conduction is not the presence of flow. It's the absence of scattering. It's the metal conspiring with quantum mechanics to ignore its own structure. Every time you use electricity, you're relying on a conspiracy. Trillions of atoms locked into perfect periodicity, scattering electron waves in such a coordinated way that the scattering cancels. The electron wave sees nothing. It propagates as if the metal were empty space, but it's not empty, it's full, packed with nuclei and fields and overlapping quantum states. And the only reason it works is because the structure is perfect enough that the interference survives. Heat disturbs it. Impurities break it. Disorder kills it. But somehow, at room temperature and a piece of copper wire you can buy at a hardware store, the conspiracy holds. You've never touched a conductor. Not really. What you call conduction is a quantum field phenomenon, a collective dance of wave functions and interference, playing out across billions of atoms simultaneously. The electron doesn't move through the metal. The metal allows the electron wave to propagate by erasing itself from the wave's perspective. Feynman understood this. He spent years teaching it, refining it, trying to make people see that the classical picture was not just incomplete, it was backward. Metals don't conduct because they're full of free space. They conduct because they're so perfectly full, so exquisitely organized that quantum mechanics has no choice but to let the waves through. And every wire, every circuit, every device you've ever used is running on that conspiracy, on the universe's willingness to make matter invisible to itself under exactly the right conditions. You thought conduction was simple. Flow, movement, electrons going from here to there. But it's not. It's interference. It's the lattice scattering the wave and then unscattering it. It's reality negotiating with quantum mechanics and coming to an arrangement that lets charge propagate despite the fact that the path is full. That's what Feynman discovered. Not a mechanism, a reframing. Conduction is not about what moves. It's about what vanishes. And the metal, dense and solid and utterly full, becomes transparent to the electron wave simply because it refuses to be anything but perfect.